So our next speaker is David Tonkin. David is a consultant who worked for a long, long time around Mount Gunson, and we're really fortunate to have him here today. He published recently 2 papers in our MESA journal, and after we read that, we said we have to have you here to give us a presentation on your recent findings on the Whyalla Sandstone. Thank you, David.
Thanks, Carmen. Just wanted to say it's nice to see the department and the other government agencies taking an interest in the Stuart Shelf again. Last time I got involved in a presentation like this, we were still using Kodak transparencies like that. Now this is a cut-down version of an article in MESA Journal from last year. I've cut the stratigraphy off it because we didn't have enough time, so it's just the petrology and the diagenesis of the mineralisation. The petrology was done by my colleague Chester Wallace, so I might not be able to answer your questions, but if you refer to the article or email Chester, I'm sure we could get them sorted out. And that's our starting point, that map. It shows 2 facies of the Whyalla Sandstone, a red one and a grey one. Now originally our thesis for the research project was that the red facies represented unaltered red beds of the Whyalla Sandstone, and that the grey was produced by the introduction of reduced oil-filled brines. Well, it turned out to be half right only. So this is what the red sandstones look like. The samples from the Woomera bore, typical Whyalla sandstone with a iron oxide matrix. This is the reduced sandstone. Thank you to Stephen Batty for this particular photograph. It shows coarse and fine-grained bimodal Whyalla sandstone. There's lamination in this case, the fine grains. And I think you can see towards the top of the photographs the famous frosting of the quartz grains in the Whyalla sandstone, which, if you look closely there, you'll see is actually quite a deep pitting rather than a frosting. Samples came from mostly drill core, quite a wide spread, as you can see on this map. All those cores are in the library here. Some more drill cores from Lucas Hill prospect, and then the rest of the samples are from the various deposits at Mount Gunson, their hand specimen samples. So what we established was a sort of a diagenetic history for the Whyalla sandstone, starting with burial diagenesis here. In this case, we still see some red coatings of iron oxide on some of the larger quartz grains there, but in general, we didn't see much preservation of the original unaltered Whyalla sandstone. This is a later stage in burial diagenesis. You see the deposition of quartz overgrowths, syntactic quartz, and separating the overgrowth from the quartz grain, you see a train of fluid-filled vacuoles, which probably represent the removed iron oxide rim. Going on to the secondary diagenesis, the most important feature of that is dissolution of quartz. In this case is showing some quite extreme dissolution of some rounded quartz grains and their overgrowths. This one's from a highly altered Whyalla sandstone in a fluid expulsion structure. The matrix here is mainly carbonate. Another example of quartz dissolution, you see that most of the quartz overgrowth has been removed on this grain, and the perimeter of the grain is extremely embayed and etched. A characteristic feature of this process is the formation of sutured quartz contacts. You see these the little red arrows indicating penetrative quartz boundaries between the overgrowths and the grains. And another version here where, gee, can I have that? Here you see quartz stylolites penetrating into the boundary of the grain, and the dotted line there represents the quartz that's been removed. Going on, the next stage is the introduction of fluorite. Fluorite filling the pore spaces between the quartz overgrowths, as you see here. And fluorite, in fact, was found in most of the nearly 50 samples we looked at least at the microscopic scale. Next mineral is barite, appears, again filling the pore spaces. In this case, the barite's accompanied by fluorite and sulphide. Next stage is chlorite, or some chloritic clays perhaps. Here you see in mantling quartz grains. A later stage is introduction of carbonate, orthogenic carbonate, filling a pore space here between quartz grains and feldspar, detrital feldspar grains. And then finally we get sulphide, introduction of sulphides. This case is incipient sulphide mineralisation. This is from Red Lake area somewhere, I think. Then we get sulphide minerals actually replacing the syntactic quartz in the pore space, and this is really the beginnings of a mineral deposit. Here we are in a mineral deposit, showing a lot of quartz dissolution textures. The overgrowths here much wider than the ones we see in burial diagenesis. And then in this particular sample you see euhedral crystal faces in the overgrowths where the invading fluid has, or later invading fluid, has etched the overgrowths back along the crystal faces. In this case, so it indicates there's two phases of fluid here, an early quartz-rich one and a later one with it's introducing the sulphide. Into some massive sulphide. This is from West Lagoon. You see the destruction of the nearly all the fine matrix quartz and replacement with sulphide, and the replacement of a lot of the syntactic quartz, and the pitting of the remaining quartz detrital grain. Then finally we get the oxidation. This is where we turned out to be wrong. The oxidation is actually a late feature. You see here quartz grains and their overgrowths are mantled by very, very fine grain iron oxides and carbonates and stuff, and giving us, if I go back, that sample from earlier on which looks so much like red bed, original red bed, is actually due to late stage introduction of oxidized fluids. So Source of the metals, we're suggesting Adelaide Rift Complex. Volcanic rocks such as the beta volcanics, arkoses, which typically can contain a range of elements we see there, reduced shales such as Tapley Hill, which introduce another range of elements including rare earths. And if you look at the cattle grid mineralisation, or even the MG14 mineralisation, this is a typical suite of minerals that you'll see in cattle grid. It's really a multi-element deposit, not just a cobalt, copper deposit. The fluids, we're saying are reduced metal-bearing brines, oil-filled brines. Those temperatures there are the temperatures at which some of these things occur. Fluid inclusions have been found at 120 by Michael Busbridge. Fluorites deposited between 100 and 150. The stylolites will form at 120. So relatively moderate temperatures. I should point out that this is kind of the reverse of the accepted theory of replacement mineralisation. We're saying it's a reduced fluid, not an oxidised fluid, and the reduced fluid has met a redox boundary where it's come across, say, the red beds of the PANDURRA formation, and indeed perhaps within the Whyalla Sandstone itself, between reduced and oxidised Whyalla Sandstone. Now that's the end of the diagenesis bit. This is just a interesting thing, a possible periglacial texture, something that Chester found in some of the sections, and he's called them clots because he doesn't have another word. They're not till pellets. Till pellets contain mostly fine-grained material. These are just typical bimodal Whyalla sandstone. And the outline of the clot is shown by sort of an annular arrangement of the longer grains there. The original, there must have been something sticking them together originally, but the original glue has gone. But we're suggesting that the most likely material was ice, and this is a periglacial feature. Yeah, how am I going for time, Carmen?
Well, if you
Hey?
close soon.
Close soon. Can I just go? I did have an end there, but look, I did stick these in. I'm just talking about, want to point out the importance of detail when you're looking at some of these structures. We've looked at some 3D pictures. This is from top of the PANDURRA formation from my database. And you can see some very steep gradients associated with mineralisation. So where can I show you? See here near Cattle Grid. This kind of shows up. Another one up there at, near Lucas Hill. And the sort of choke points that might be important in the deposition of mineralisation. The second one from my database is ISOPACHS for the Whyalla Sandstone, and you can see there some steeper gradient areas which again would represent potential choke points for mineralisation, and those might well coincide with the top of the PANDURRA slope. Yeah, and that's all. Thank you.